Click. Welcome back, suckers. You're going to get the short and fast version of the syllabus and schedule talk because you all had me before. You know all this crap. The only new stuff is, the office hours change. Monday, Wednesday, Friday, 10:20. Tuesday in the morning, Thursday morning and afternoon. They're all over the Richmond Center, just like they've been for the past few years. And there's the Google Meet if you want to do that. Office is still downstairs, but you'll find me over there far more often. The textbook. Do you all get a physical copy or an e-copy? Do you have access to it on Canvas through the book bundle, or did you all opt out? Okay, you gotta go get it. Yeah. We're going to use this a lot. You have the book. And since it's already part of the book bundle, it's free. You've paid for it already. Go get the book. But there's, physically go pick it up if you need the hard copy, which I think was what was requested for this course. I know they got them in. I was there when they arrived. As a majors course, there's the program objectives. We're going to do a bunch of stuff. It's all particular to differential equations, which you've seen in Calc 2. So the beginning of this course is going to be familiar stuff. We're just going to take it a little further. All of the policies are effectively the same as they've been in every other course. Come to class, turn in physical homework. I want paper. I promise I'll put up the grades, the keys and the grades through Canvas the same way. Now they did change something in Canvas. The attendance policy now does have an excused version. So this sentence on your electronic copy got changed. So I can mark excused absences versus unexcused on Canvas. Attendance is now required to be taken there. So I'll make sure it gets in there. Do the homework. Turn in nice, neat assignments. 4 exams. There's one. In-semester exams and the comprehensive final. It's going to be just like every other course you've taken with me. I promise it won't quite be as sadistic as some, but different people have different opinions on the material. I do recommend a graphing calculator. We'll use a lot of particular graphs, but there are several other apps we'll use. There are links to a bunch of stuff in our Canvas page down here. The Slopes app for iOS or Android is available. That allows you to create some of the graphs we're really going to use a lot of and make them touch sensitive. You drag stuff around. You can do all sorts of very neat things. It's worth having. You can run it on a PC. I don't know if it can run on the MacBook as a standalone. I don't think the iOS version is a Mac OS version, but that Slopes app is very useful. If you want to connect your calculator to a computer, which you can then use a USB-C cable or a USB-A cable, mini, to connect to your calculator, you can send programs to your calculator. Things like the error function, the completion of the error function are available. I put them here. We'll get to a bunch of these programs as we go along. There'll be a lot of places where I want you to use Wolfram Alpha. I want you to use Desmos or something like that, because it's just a pain in the ass to graph by hand or to work out this, 7 systems of 7 equations and 7 variables by hand. And despite what Linear told me about those being easy, they're not always. Again, the graphing calc will be the only thing you have during the exams, which means I'm going to rig the exam questions to be reasonably doable and not insane. Grade distribution, grading scale. Everything down here is stuff you've seen in my other classes. Class is designed face-to-face. Make sure you don't block the exit if we have to get out of here. Hurry, there's a stairwell in the back corner on the far side of the physics room, as well as the central staircase. We'll see what's available if we have to get out of here in a hurry. But please make sure you don't block the aisle if you have to get out. You'll get starfish updates occasionally. There are at least 3 that are required, plus whatever I feel like sending about. Please send me email as a first resort. I'm unavailable in the middle of the night, so you'll get stuff the next morning. If you're going to miss for any reason, call me, leave a message on the phone number at the beginning. It'll convert to a voicemail. I'll get a timestamped voicemail recording of your message. We've got a schedule. You know what we're going to do and when we're going to do it. I will say, I think this is the class. Yes. Tuesday exam. So we get it relatively early. No extra credit assignments. If I'm rambling, it's because somebody's still looking at me like, what? And I'm going to fix that. Valid email address needs to be everywhere. I won't be able to memorize whose email address is what. It'll send to your Seton Hill by default. If you forward that, that's fine. I'll respond to any email you send me. But when I go to look something up, it's going to go to send to you. It's going to go to your Seton Hill account. Please make sure your phone's on silent or vibrate during class. If your crotch is glowing because you're texting in your lap, I'm worried you're getting radiation in weird places. Don't do that. No tobacco use in the classroom. I am a mandatory Title IX reporter. If I am told about or witness harassment of any type, sexual harassment, dating violence, domestic, any of that, I am required to report it. Shouldn't stop you from telling me stuff, but if you want to talk to somebody who is not required to notify people, call the Blackburn Center or Counseling Center, Marriage and Family Therapy, or Campus Ministry. But if I observe or am told, I am mandated to report that. Disability services, if you have accommodations, let me know as soon as possible. ODS is on 5th admin. Get them to send me whatever is needed to accommodate, and we'll make it happen. I am recording the lecture. The Zoom is being recorded. It will get uploaded to YouTube. There will be a link on our Canvas page. So if you're going to miss class, well, you'll have the ability to do the recording. Just like in my previous classes, anything I write will get scanned and uploaded as well. Academic engagement. Come to class, do as much of your own work as possible. I am 100% sure every problem in this textbook is Googleable. That doesn't mean that should be your first resort. Academic honesty, don't cheat. Work with each other. I want you to work with each other. I think that's helpful. I think it's beneficial. I think it gets you a better access to pieces of information you may think you're clear on or may not be clear on with each other. I think that's useful and helpful. This is going to be the same as every other semester you've had with me. So if you've got questions, ask them now. An important point. Almost all of my 4-day-week classes meet Monday, Wednesday, Thursday, Friday. Not this one. We meet tomorrow. We meet tomorrow over in admin, not here. We're in admin 308 on Tuesdays. It is 12:45 to 2. It is a 75-minute period on Tuesdays, not a 50-minute period. I tried to make it so we'd get Tuesday and Thursday. They wouldn't give it to me. I wanted to make a lab. Well, then we could do all the stuff on the computer in class time, and it would be much more useful. They wouldn't give it to me. Questions? Same to you. First 7 chapters of this. What that means? We're going to start. Here we go. A lot of this beginning comes almost the same, paraphrasing from chapter 9 in the Stewart Calculus book back in Calc 2. So I know the majority of this should be familiar at a basic level, but we're going to push quite a lot of this. So if I give you an equation, you know how to take its derivative. whether that equation is given explicitly, like this one, and this is fortunate that I cheated and this is just power rule, or if that equation is given implicitly. Usually these are set equal to a number. So I'm going to go ahead and do that. I could ask you to try and solve this equation for y and then take its derivative, or I could use implicit derivatives, chapter 3 something, 3.6, 3.5, somewhere back there in Calc 1. We did that. I can still figure out dy dx here. I know how to take a derivative. I want to go backwards. If I have something like this, I could ask you, what's the original equation? Right? You know how to do that. I undo a derivative, that's a piece of cake. It would be nice if I had some more information, otherwise I'm going to get those constants of integration, right? I do the antiderivative, I get a plus c. But that's y prime because I have a second derivative over there on the left, which means I'm going to have to do the antiderivative again. I'm going to get a different constant. So I have a plus c and a plus d. And I get all sorts. If I had more information, then I could actually figure out values for those numbers, right? But what if I have an implicit equation? I got y's on both sides. The hell is this? Well, this equation is a new attack. A differential equation is any equation containing a function and one or more of its derivatives with respect to one or more independent variables. This only has one independent variable, x. I could have a function of two independent variables. The way we determine or classify a differential equation depends on three real things. Differential equation, I'm going to abbreviate that DE. My three main descriptors are type, order, and linearity. So I want to know what type of differential equation I have. What order is that differential equation? And is that linear? So those are the three questions I need to answer about any given differential equation. So let's start with type. The type depends on the number of independent variables. If I have one independent variable, that's called an ordinary differential equation. This is what we did in Calc 2. Back in chapter 9, in Calc 2, we dealt with functions of one variable. But what do we do in Calc 3? Multivariate, right? We had multiple variables. A partial differential equation Has multiple independent variables. So an ordinary differential equation will end up only involving one y of x. So something like any of these three equations. The third one's a little interesting. First one, y prime plus 5y equals e to the x. X is my independent variable. Y is the function of that independent variable. I have the first derivative added to a multiple of the original function, I get e to the x. Here, in this second equation, y double prime minus y prime plus 6y equals 0. I don't have anything about x, do I? But I'm assuming y is a function of something. It could be x, it could be t, it could be whatever, but it's a function of one variable because this notation y prime refers to the first derivative with respect to a single variable. But down here, I've got dx dt and dy dt. Isn't that more than one variable? It's more than one function. X of t, y of t, but they're both functions of a single variable t. It's one independent variable. It's multiple dependent variables. And that's an important difference. What I've got here is still ordinary because everything is a function of t. And those are ordinary differential equations, ODE. A partial differential equation is going to have partial derivatives in it, functions with respect to x and y, right? So here, I've got an equation like this. uxx plus uyy equals 0. Ux equals vy. I've got two different functions and two different variables. Uh-oh, that's okay. Second partial derivative of u with respect to x twice plus alpha squared, second derivative of u with respect to y twice equals 0. I can use whichever notation you like. I use the subscripts. I use this Leibniz notation with the partials. I can use primes like Fermat did. If I really want to be particular, I could use dots above my functions instead of primes to represent that second derivative. You get a y with two dots over it. That actually was Newton's original notation for a derivative. The dot above the equation. That was the fluxions notation in his original writing. A lot of that is seen more in the physics work than it is in the math work, so we won't do a lot of dot notation. But if you read a physics differential equations paper, you'll see that a lot. These two equations, uxx plus uyy equals 0, this is the same uxx, the second derivative with respect to x. This is the same second derivative with respect to y. There's this number here being multiplied. The only difference between these two is that number. These show up in chemistry and physics a lot. These are the wave equation and the heat equation. So when you talk about an object vibrating, where you are along the string and where you are in the vibration, it's x and y, right? In thermodynamics, I'm heating something from some point along a rod. Well, where I am and how long it's been. X for my direction along the rod, y for the time. Okay, so that's type, ordinary differential equations, partial differential equations. This course will almost exclusively talk about ordinary differential equations. There are a lot more different and weird techniques for partial differential equations whose basis is the technique from ordinary equations. So I want to start there. If I was doing differential equations too, that would be partial differential equations. We're not doing that. So type is first. What was the second one? Say again? Order. So order, that's a term I've heard before. As a matter of fact, I just used it here. What's that symbol? Oh, that whole fraction thing. Yes, that's dy squared. But this whole expression, this fraction, a second order derivative. Order measures how many derivatives are taking. As a matter of fact, if you think about it, we called it the first derivative, the second derivative, the third derivative. Those are order numbers, aren't they? It's not the one derivative, the two derivative, the three. It's an order. First, second, third. So when I talk about order here, I'm talking about the order of the derivatives. That means in the examples that are up here, I've got first order differential equations, 1, 2, 3. Those all have only first derivatives. And I've got second order differential equations, 1, 2, 3. It is the highest derivative that gives me the order. So the fact that there is both a first and second derivative in here makes this a second order differential equation. But I'm looking at derivatives. I stole this equation directly out of the textbook. Matter of fact, I think this is problem 3. Could be wrong. I'm making an assumption here. The assumption I am making is that y is a function of t, not a function of x. Assuming that is the correct assumption, what order is this differential equation? Because that's the Roman numeral 4 up there, right? They stop using primes after a while. Too many of them in a row, I lose count. After 3, we just start using the Roman numerals instead. So that's a fourth order differential equation. An ordinary differential equation. Again, they changed my dependent variable on me. Sine theta y triple prime minus cosine theta y prime equals 2. A third order differential equation. And that's why I needed the parentheses, because if I write cosine theta y, is the y part of the argument of cosine or not? I need to be explicit when I write these sorts of things. And then here's a first order differential equation. Same one we had earlier. Questions? Okay. I look at all three of these and I realize I wrote them all in the same notation. I wrote them all in that Fermat notation with the primes. There are many more occasions when I prefer to use the Leibniz version with dy dx. So I'm going to take this equation, I'm going to rewrite it. With dy dx. Now you may ask yourself, why would you do such a stupid thing, Dr. Sassmore? That's less pretty. I don't like dy dx anywhere near as much as I like y prime. And I understand that. But again, back in Calc 1, I remember using dy and dx like they were separate pieces. When we did integrals, right, we did u substitution, we'd write du dx and we'd move the dx to the other side to rearrange stuff in our antiderivatives. I did that a lot. I want to do it here too. I'm going to take that e to the x that's over there on the right, move it over to the left. And then I'm going to use the dy dx as if they were separate pieces. I move this way. And then I'm going to multiply everything by dx. And now I have a function times dy and a function times dx. The function that happens to be times dy is a 1, but that's okay. 1 dy plus stuff dx. X comes before y. Let's write these in the other order. All I did was switch sides. And I put the 1 in there. That's optional. You don't have to put the 1 in there. But when I write an equation like this is called the differential form of my equation. I've lost my memory. How many of you took linear with me as opposed to took it with Dr. McNabb? Okay, you all took it with Dr. McNabb. You took it with me? Okay. At the very end of linear, I talked about quadratic forms. Same idea, only this is a differential form because the differentials are floating around in it. It's a new way of writing our expression to emphasize the differentials. In general, we'll have some function of x and y times dx and some other function of x and y times dy. And most commonly, we use m and n. Not required, but typical. It is often worthwhile to switch back and forth depending on whether we can write dy dx nicely alone in terms of other things or whether we can't. But quite often, when we have, as we did at the beginning, you gonna be a pain in my neck again today? Yes, you are. Okay. You go over there. Here's a non-differential form of my equation. What I like about this version, first of all, it's equal to 0. But second of all, it's fairly easy to convert from this notation to the differential form. But when we see it written like this, we sometimes think of this as some big function of x, y, and y prime. Please notice that implicitly right there tells me the order of this differential equation. This is first order, because the highest derivative is y prime. It could also involve y and x, but there you go. Right? Convert that from this form to the differential form for me, please. There we go. Just scribbling to make sure my pen was working again. You can ignore that. What do you get for the normal version of this? Yeah. So there's m of xy and there's n of xy. Perfect. Really, you just change this to dy dx, realize this is the only thing with the dy, so this whole thing is going to get the dx. There's another version of this equation. I can take this same equation and rewrite it to get y prime all alone. If I can isolate the highest derivative, that's called the normal form of my equation. Now, in this case, when I go to do that, I'm going to have to divide. And that does mean I'm going to have to play some algebra games and make sure I'm not dividing by 0. So when I rewrite this, y prime equals negative x squared plus y squared over 6xy. Just like we had this expression reading capital F of x, y prime equals 0 as our implied form, I can think of this as y prime as a function of the other pieces. If I have a second derivative, it'd be y double prime all alone. Again, sometimes the algebra is not very nice. So we'll have to make sure these are rigged. Questions? What's my third? Oh, yeah. Type, order, is it linear? Linearity. Um, um, huh? This is the formal definition of what it means to be linear. An ordinary differential equation is linear if the function capital F is linear in the variables y, y prime up to y to the nth. That's our nth derivative. So this is an nth order equation. What the hell does it mean to be linear in these variables? Linear algebra. I'm back to linear algebra. We did this. What's it mean for an equation to be linear? Back in linear algebra. Standard definition that we used the very first week in linear algebra. Unfortunately, no, because the linearity doesn't apply to the solutions. It applies to the equation we're setting up. Because a bunch of stuff we did in linear had infinite many solutions, right? I don't want to classify my solutions yet. It was a long time ago in a galaxy far, far away, I understand. When we wrote the equations in x1, x2, x3, up to whatever, right? What could be in front of those things? Nothing but numbers. We could never have the x's multiplied with each other. We couldn't have like an e to the x floating around in there. The only thing that the variable x1 could have in front of it was a number. But positive or negative, rational, irrational, doesn't matter. It could only have a number in front of it. All of these variables can only have things that aren't other of those variables. What's missing from that list? That was up in our function f. It's missing from this list down here. It's up on the top of the screen in that f, but it's not at the bottom of the screen in the list. X. I need to be linear in the y's. So y can't be multiplied with y prime or y double prime. It can't be added to some cosine of y or e to the y double prime, but it could have x's in it. And that means that a differential equation is linear if it looks like some function of x times the nth derivative, some other function of x times the n minus first derivative, some function a1 of x times the first derivative, plus a0 of x times the naught derivative. And there could be a function of x all alone. If there is a function of x all alone, I'm going to put it on the other side of the equal sign. This is what it means to be linear. The only thing that is multiplied by any of these y's, which all appear to the first power, just like they did in linear algebra, is a function that has nothing to do with y. Most often, these are going to be numbers. Wait a minute. Let me back up to the examples we did earlier. This is a linear second order differential equation. What's multiplied in front of the y double prime? 1, -1, 6. My coefficients are all functions that have nothing to do with y. As a matter of fact, all of these are linear. This one is also linear, a function of x times y. So a nonlinear equation is just one that's not linear, something like this. That's not linear because I've got a product y times y prime right here. Or if I write something like this, that's not linear. That's sine of y. If I wrote y squared instead of y second derivative, that would be nonlinear. I really, really, really like linear equations. Linear equations are much, much easier to solve than nonlinear equations. Nonlinear equations are the stuff of which nightmares are made of. We will avoid them at all costs. When we can't avoid them, we'll learn how to approximate them with linear equations. How do we approximate something ugly? We make it nicer. Oh, wait a minute. Nice thing. I think in calculus terms. Nice things are things like polynomials. But I need really big polynomials, which means if I really want to approximate something, I'm going to end up using a power series. We're going to need a lot of stuff from Calc 2, people. Lots of stuff from Calc 2. Fortunately, series are not until much later in the course. You have time to review, but we will be doing them. Questions? What's it mean to solve a differential equation? To solve a differential equation requires you to have two things. It requires you to have a function y of whatever that you can plug in and it will make the resulting expression true on some interval. That's the second part of it. If I'm solving a second order differential equation, I need my function phi to have at least two derivatives. If I'm solving a third order differential equation, I need phi to have three derivatives, so on and so forth. They called the phi I stole because that's the symbol they use in the book. I was calling it y earlier, right? I want some equation y of x, phi of x, f of x. I don't care what you want to call it. I need an equation that I can plug in to my differential equation and say, hey, when I use this, it works on some interval. Sometimes that interval is the entire real line. Sometimes it's only a particular range of numbers. We will have to use information about those A functions up there to tell us about the interval. So, as an example, on the entire real line, I claim that works. Phi of x is e to the negative x over 2. This function is defined everywhere. All values of x, the domain, goes from minus infinity to infinity. What's y prime? Phi prime. Take a derivative. Welcome to day one. We've got to be able to do calc. Chain rule. Yes. Hey, wait a minute. If I put that in where y prime is, and I put this in where y is, do I get 0? So I put the derivative in. I put the original function in. What happens? I hope so. Otherwise, it's not a solution, right? Hey, the 2 and the 1/2 are going to cancel. Then this will be negative e to the minus x over 2. This is positive. Those cancel out as well. Yes, this is 0. Exactly what I wanted. I could graph this equation, right? You can take this equation and you can graph it. Graphing a solution, I hope this surprises no one, is called a solution curve. But please notice, not only does this equation work, so does this equation. As well as this one. All of those work for any number you want. What happens when you take the derivative of any one of these? You basically just take the derivative e to the minus x over 2 and then stick the number in front of it, right? So the 3 would be inside this set of parentheses and inside this set of parentheses. It would still cancel out, wouldn't it? So we really don't just have one solution. We have infinitely many solutions. They all differ by having some constant multiplied on them. So really, there's our set of solutions. By the way, if I make k equal to 0, a horizontal line, it still works. K could be positive, K could be negative, doesn't matter. I'm running up against the time here. There's an example in page 7, example 6, where when we go to look at our differential equation, we have a 1 over x in it. If I have 1 over x, what's next? Not allowed to be. Which means either my interval is negative numbers or positive numbers, but it can't be both because the function would be undefined at 0. So my interval will then depend on what information I'm given. I'm given information about a positive x or negative x. This solution is an explicit equation. Y equals stuff in x. Sometimes I end up with equations that are implicit, just like we took implicit derivatives. When we're doing problems for this course, you only have to get an explicit solution if I ask for one. Otherwise, an implicit is fine. Example 7 walks through example like that as well. This is a parameter. It's a number we have control over, choice over. A lot of our differential equations will be families with parameters in them. Remember when I was talking about the one at the beginning? The second derivative equal to a number. And if I wanted to solve that, I had to integrate twice. I was going to get 2 different plus c's. That's a 2-parameter family. We can have as many different parameters as we need in our solution sets. I recommend to read through this section to internalize the terminology, because it's going to come very thoroughly as we move forward. There's something missing here. How do I figure out what K is? Guess what we'll talk about tomorrow. Tomorrow we're over in admin. I will see you all over there at 12:45. Wonderful rest of the day. Push stop recording now.